Today we're going to take a deeper look into the data part of data science. And we're going to start by focusing on structured versus unstructured data. These are terms that you've probably used, but we want to make sure you understand all the nuances and the formats and ways that you're going to encounter data in both of these forms. So structured versus unstructured data. Structured data is really the data that you're lucky to have if you're able to get it. It's well organized. It's usually very straightforward to put it into a database. Typically, this comes in the forms of tables where you have rows and columns. Each column represents a different attribute. Each row tends to represent an entity. There's often a schema, and schemas define what are those attributes, what do they mean, are there rules, can they only be applied to certain types of entities, and so on. So these data tables typically are nicely structured. There's a lot of numeric values often, and it's really easy to process them and then do analysis on them automatically. Unstructured data, basically everything else. And there's a ton of this kind of data out there. The challenge is when we're encountering data is to figure out what structure exists, if there is any, and if there's not, to try to impose some sort of structure. So we can sometimes take our unstructured data and put a little bit of metadata with that to make it semi-structured. Sometimes it comes with that kind of data. And so we're going to talk about all of that today, look at some real examples that are out there on the web to understand what you're going to encounter and how you can deal with it. So let's start with structured data. I want to talk about the data formats that you're most likely to run into. There are an infinite number because people often come up with their own, but there are also some standard ones that you'll want to be aware of. JSON is one of the most popular at this point. JSON is a standardized format, and it's basically a really compact way of representing name-value pairs. So you have the name of an attribute that you're interested in, and then you have the value that goes with that. You can also have objects here, which you know from object-oriented programming. So, for example, if we're looking at Twitter data, you can have the data for a tweet. That tweet would be an object, and then you have a bunch of name-value pairs that'll include things like the text of the tweet, the screen name of the person who posted it, the timestamp where it was posted. And so JSON will have a container for that object, and then it will have all those name-value pairs. It'll say screen name, colon, whoever the name is, text, colon, the text of the tweet, and so on. So you have a bunch of those attributes. One of the benefits is that it's a really concise format. So today what I want to do is actually show you examples of a lot of these different formats out there on the web. JSON is one that's very easy to find. What we're looking at here is data from the Open Weather Map. So this is an API for accessing weather data. And what it's giving here is the weather for a certain area. What we're looking at here is in JSON format. It's pretty concise. You can see that there are name-value pairs. So we have coord, those are coordinates, and then a colon followed by the value. The value itself has subparts, a longitude and a latitude. Then we have the weather, and there's a bunch of subparts of that as well. It's a little hard to read in this format, so we could click on Pretty Print, and that's going to format it a little bit more nicely for us. Basically, it just indents. JSON doesn't care about white space, so like many web formats, you can put in as much as you want. Now we can read this a little more clearly, and part of the benefit of JSON is that it's intended to be relatively easy for humans to read compared to other data formats. So we start with the attribute coord. That's always followed by a colon, and then it can have a value directly after it, which we see here, or it can have a set of curly braces which contain basically a sub-object. It doesn't get a name like it would in object-oriented programming, but it's basically a collection of additional attribute name-value pairs. So for coordinates, we have then subparts longitude and latitude with their values. After each name-value pair, so here the name would be coordinates, the value would be this little object, we do a comma. Weather is our next attribute in a colon. And then we have square brackets. These are used when you have a list of things. Now there's only one thing in our list here, but sometimes you'll get like a 7-day forecast from this website. And so inside the square brackets, you would have 7 of these blocks that have the different days worth of weather. Here we have a list with just one thing in it. That's an object, again, and it has 4 attributes: ID, the main weather, which is clouds, a description, which is scattered clouds, and then an icon. We don't know what that is, but it's probably something that they use to actually pull the correct icon out when they show this graphically. For base, we have stations. For main, we have another object, and so on. And so you can see that there's a pretty consistent format here. It's always a name-value pair. Everything's in quotes. There's a colon between the name and the value can be just a number, a string of text, or it can be an object or an array, which is what we saw with the square brackets here. Your browser actually knows how to show this nicely, so we're looking at this under raw data right now, but if we click on JSON, it actually parses it out for us in this really beautiful way. So this is parsed. This is not what raw JSON looks like. That's what we were looking at here. But this is a format that is really easy to work with. Whatever your favorite programming language is will have a library that can automatically read in JSON and turn it into a data structure that you can work with. And it's really popular as a way to provide results from web-based APIs because it's concise. It's a very compact format. So that's JSON. It's something that you're going to run into quite a bit. If we had to pick another one, it would be XML as one of the most common formats that you'll run into. XML stands for the Extensible Markup Language. This is what HTML is based on. The language is used to make web pages. It's also used just to represent data. And a lot of APIs will provide their results either in JSON or XML format. XML uses tags like HTML does, which you've probably run into. It takes up a little bit more space than JSON because you have start and end tags, and of course there's all the little brackets in there, so it's a little bit hard to read, but it's really common to see. So if we flip back to my browser here, close out our JSON, what I'm looking at here is the XKCD website, these kind of techie web comics, and this has an RSS feed. So RSS stands for really simple syndication. And it's a way that you can subscribe to a website. It's often used with blogs. It's also the basis for podcasting. Podcasts are basically RSS feeds that link to MP3 files. So it's a way to show when you have updates to your site. The RSS format is usually provided in XML. So if we go to their RSS page, which I had pulled up here, our browser actually knows how to process RSS, and so it's giving us a little message, hey, this is an RSS feed, and it's showing us something that looks a lot like that web page. That's because the browser is hiding the RSS XML code from us. So if we go to view source for that, again, this is not in a nice format. We'll fix this in a second to make it look nice. But what you can see is that we have a bunch of tags. This is what XML looks like. It has tags like this, a start tag, and then an end tag, which is the same thing with the /. The value goes in the middle, and we have a whole bunch of stuff here. What I'm going to do is copy all that. I'm going to pop this into the online JavaScript beautifier, which actually formats a lot of different things for us, not just JavaScript. And that has given us this nice formatting of the XML. That's probably a little small for you, so let's zoom that in. So now we can see for our XML that we have some information in the headers. We have information on our channel. It has a title, it's xkcd.com, a link, a description, and then we have these blocks called items. And items basically are used in RSS to tell us when we have a new page, basically a new post. So RSS uses XML, which is the format here. XML is the tags that have names. They sometimes have attributes in them, name value pairs like this. They have a start and an end like we see here, the title tag and the end title tag. That's the basis of XML. RSS is a schema on top of XML, which basically defines here are the specific tags that we're going to be able to understand. So if you want to process RSS, you need to understand these tags. It uses the XML format, and in this case, items represent new posts on the website, and each one comes with a title, a link, a description, a date, and then sometimes this attribute guide, which basically is often the same thing as the link. So, really common to have this in XML format. So just to be clear, XML is this format with tags. There's start and end tags. There can be attributes inside the tags, and the values go between the tags here. You can put lots of schemas on top of it. So HTML is a schema, RSS is a schema, and those define specific tags to recognize. So XML is the format, and then the schemas define specific tags that will work. You can make up your own XML schemas though. You can use this kind of tag structure to come up with your own tag names, your own attribute names, and process them yourself if you want to. What you're likely to run into is that websites will either be using a predefined schema like RSS, or they'll have their own that defines each of those attributes that you can expect to see. So JSON and XML, by far the most common format that you'll find data provided to you in, especially if it's coming out of an API where you're accessing a website and requesting data. It's nice because it gives you data in a nicely structured format. You can see easily how you would parse that data that I've provided and get it into some kind of table form that you could use, say, in a database. Building on XML, and we're not going to go deep into this, but I just want to mention there's a thing called RDF. This stands for Resource Description Framework. It's the kind of base language of the semantic web, which is designed to create machine readable representations of the content of web pages of databases. So RDF is based on XML, but you can create your own schemas that actually have a whole bunch of logic built into them. So you can say these attributes can only be used on objects of this type, similar to the kind of structure that you get in an object-oriented programming language where you define objects, you define the attributes that go with them. You can make all kinds of conclusions based on that. It's really interesting. It's more complex than we want to get to in this course, but if you're interested in knowledge representation, RDF is definitely something to look into. Next, we have CSVs and TDFs or TDVs. So CSVs are comma-separated values. TDF is typically used to mean a tab-delimited file, or you sometimes will see TDV for tab-delimited values. So these are documents where essentially you have a table of data already, and the cells in a row are divided by commas in a CSV or by tabs in a tab-delimited file. These are pretty nice to work with. They're really easy to parse. Lots of tools can parse them for you. Excel, for example, can read comma-separated or tab-separated files. You're really lucky if you get data in this format. It is a little bit less flexible than JSON and XML because you have to have a predefined set of column names, where with JSON you can have as many as you want. Different objects can have different ones. But it's great if you actually, as a data scientist, get data in this format because it's super easy to bring it into whatever tool you're using and to process it. So just be aware, you will get a lot of data sets provided to you in CSV or tab-delimited format TDF. And then there's all kind of custom formats out there. So JSON, XML, RDF, these are all standards. CSV and TDF, they're a little bit simpler, right? It's basically just there's commas in between your columns, or there's tabs between your columns. It's not a really rich format. But there's all kinds of other ways that people choose to represent their data. I was just going through my folder of data sets, and this is one example. This is a data set of the student government at this university. It's in PIEC format. PIEC is a tool that you use to visualize social networks. It's not what we're using in this class. We have a more modern one that we're using, but it's kind of a classic one. So this is representing social network data. It has here a matrix. So basically, what we're looking at here is that there are 11 people, and they're numbered here from lines 7 through 17. And our matrix here has 11 rows and 11 columns. And so what this first space means is that has person 1 engaged with person 1 with themselves. So we have that marked as a 0. We have a 1 that says yes, they have engaged with person 2 and 3, a 0 and another 0, so they have not engaged with ministers 4 and 5. They have with 6, not with 7, and not with advisors 1, 2, and 3. So we have a sort of matrix of interactions down here. And these are labeled like this is the actual data set. So we have a network name, a number of vertices, some information about the people, this tag matrix, and then the matrix. And if we scroll down, here's another network with more information in another matrix. This is a structured data format. There's a clear structure here, but it's very specific, right? It's not in any of these standardized formats. If you want to process this, you either need to be using the PyEC tool that knows how to deal with it, or you essentially have to write your own processor because it's a really specific format designed for use with that one tool. So it is structured data, but you need to kind of wrangle it into a format that's going to be usable. That's also something that you have to do with unstructured data. We're going to do some examples of that later in this lecture, but this will be a common thing where you'll get structured data, but in a format that someone has just come up with. It's predictable, but it's not usable like it is, and you'll have to turn it into something usable. Okay, so let's go on and talk about unstructured data. What is it? So we've been talking about data that's structured. It comes in a nice format. It's relatively easy to get in a database. Unstructured data, basically all the other stuff that's out there, and there is a ton of it. So any kind of text will count as unstructured data. Sure, there's some structure to text, but it's not a structure where we can, say, have a tweet that I've written and easily take the meaning of that and put it into a database. We could take the whole blob of text and put it into a database, but the information that's contained in that text is not easily parsed out. So text counts as unstructured. Images and video, again, there's a structure to make that file, but the data that's, say, in an image, who's in there, what's the setting, who's talking to whom, what's going on, what time was it taken. You may be able to tell that by looking at the image, but that data is not structured. So really what you have is the picture. So unstructured data is referring to all of these formats where the information may be there, but it's not represented in a way that you can easily just stick it in a database and capture all the meaning of the data that's in the file. There's a ton of this online. There are a lot of tools that kind of help us work with this. So we'll see when we get into some more machine learning that we can do machine learning by basically counting the number of words and how many times each word appears in a document and using that basically as structure. So our attributes become every word that's ever been used, and the values that go with that is how often is it used in a particular document. It's kind of turning unstructured data into something a little bit structured. It does not capture all the meaning that's there, but it gives us something that we can work with. You can also do this with images, video, sound files, log files, but you're kind of creating that structure. You're deciding what the attributes should be and what values they should have. And it's not something that is predetermined. Somebody else could come up with a different set of attributes depending on what they're interested in. You also get a little bit more information if you have semi-structured data, which would be any of these unstructured formats that may come with something else to give you a little bit of insight. Often that comes in the form of metadata. So metadata is just data about other data. You can have structured metadata about unstructured data. One common example is a format called EXIF, which is an XML format to represent metadata about images. So the metadata will be things like potentially where was the photo taken if it's GPS tagged, what time was it taken, what sort of camera was used, and a lot of that's embedded in the image itself. So you can look at the image, but if you open it up in a viewer, you also can see this metadata, which is structured. So I'm going to just give you a quick peek at that. What I've put in here is just an image from my dog's Twitter feed into this tool called EXIF Data, and I'm going to submit it. And that has given us some of the EXIF data, the structured metadata about the image. Let me zoom in so we can see that a little better. So it's showing us the image here. And then here are all of these attributes that are part of EXIF. It's not obviously showing an XML format here. It's showing in a way that humans can read it more nicely. But you can see that we have a fixed set of attributes here. So file size, type, MIME type, image width, height, and so on. So it's giving us all of this data. That's not the only data that we can get with EXIF, but it's everything that's available for this image. So now let's talk about data wrangling. Once you get whatever data you have, how do you transform that into a format you can use? And of course, the answer to this entirely depends on what format you get your data in. There's not a hard and fast set of rules, especially when you're working with unstructured data. But part of being a data scientist is being able to solve this problem. Where you're given data in a strange format and you want to figure out how you can use the tools at your disposal and use your critical thinking to turn it into something manageable. Part of what we're going to use here are regular expressions. So regular expressions allow you to express patterns of text. So normally if you have a text document open, you can do a search and you could search for, say, AA. So you're going to search for any place in the text that two A's show up next to each other. That's fine. We know how to do searches like that. Regular expressions allow you to search for a pattern. So you could search for, say, any two digits that appear in a row. Or for the letter A followed by any letter followed by another A. And so you're not looking for a specific phrase. You're allowed to put in some wildcards, any letter, any character. Maybe a digit followed by a dash followed by another digit. Regular expressions look something like this. This one's a little bit complicated. It's a joke if you know regular expressions. Basically, regular expressions always appear with the forward slashes on either side, and the pattern goes in the middle. The letters that you're looking for will appear in there. So here I'm looking for two B's. This vertical bar is an OR, kind of like you're used to double vertical bars in programming to mean OR in a conditional statement. The square brackets that start with a caret and the inside means not the characters that follow. So square brackets with a caret and a B, and the closed square brackets mean any character that's not the letter B. And then the curly braces afterwards with a number indicate how many of those. So what this regular expression actually says is two B's or not two B's. Apologies for the bad joke, but it's a good one to show off. Essentially, regular expressions are looking for patterns of characters. They're normally much simpler than the one that we have here, unless you really get into them. And they're really useful for search and replace. I want you to do some programming. I want you to get a handle on the tools that are available for you, but I also don't want you to underestimate the power of fancy searching and replacing. If you have reasonably sized data, you can actually do that in your text editor. We're going to go through an example of that now. But even taking a little sample of your data and figuring out regular expressions that will work in your text editor, then allow you to translate those into your programming language, because all programming languages support regular expressions. Instead of giving you a full-on lecture of all of the different characters, I have put some notes on this up on the Canvas website for today, because there's just a handful of different wildcards and things that you can use. So I'd like you all to review that before we move on to the example, but it's not worth it for me to just put them all up on slides. It's really handy to have a printed out reference in front of you. So go ahead, grab those notes, print that out, give it a read. And now what we're going to do, so you should pause the video, I'm going to show you how you can use these regular expressions in your text editor. So I have a Mac, I'm using BBEdit, it's my favorite editor. This also works in Sublime Text, which works on all platforms, and any kind of programming-oriented plain text editor probably has the capability to do search and replace with regular expressions. What we're going to do is take this ugly data file that I have here, and we're going to turn it into a nice structured formatted data file. So first, let me save this. What we're looking at here is NHL data, and so I'm just going to save this as nhl.txt. I will eventually show you where I got this from, but often you're just given data like this. Someone may have copied and pasted it from somewhere. It may have just been spit out by some tool in this format, and you need to go through and look for patterns in the data to figure out what the structure should be. So what we can see here is that we have a number, then we clearly have somebody's name, 2017 to 2018, a three-digit code, a three-letter code, a one-letter code, and then a bunch of numbers. And here we've got another name. It has, the first person had 1, this person has 2. Again, we see 2017 to 18, three-letter code, one-letter code, and a bunch of numbers. Here's another name. This person's number 3. So we're starting to see the first was 1, the second was 2, this is 3. So that's probably an index, a code just indicating where they are on the list. We have a name, 2017 to 2018, 3 letters, 1 letter, and a bunch of numbers. And so now we can see that this pattern is here. We have what number are they in the list. We have a name. We have probably the season, 2017 to 18, 3-letter code, 1-letter code, and a bunch of numbers. So now we can kind of break this data up into an entry. If we highlight this, this is the data for one person, most likely. And that, except not with the 2, just this here. And then the 2 numbers are next person, and what follows is probably that person's data. So what we want to do is get this either into a comma or a tab separated format where all this data is on one line. All right, so to do that, we could get rid of all the new lines, but then everybody's data would be on one line, which isn't what we want. We want to have this digit, this number, followed by the name. We know that's the beginning of a line. So these digits aren't going to be helpful because there's a bunch of numbers all over in here, and it would be really hard for us to know when have we encountered, a digit that just happens to be the right one. The names are pretty unique though. Scrolling through the data, there's all these names. They all have a space in them because there's a first and a last name. None of the other data here has a white space, it looks like. And so if we find some unique thing like that, and there's plenty of other ways to do this, but that's one, we can use that to help see if we're on the right track, and that may be an indicator where we can grab on and use something interesting. So the first thing I want to do if I come up with a theory like that is to test it out. So my theory is that the only place that like a white space character shows up is in players' names. So what I'm going to do is search this file for just a white space. I've just typed the space bar there. And I'm going to do find all. And it's going to give me a list of all the matches. And what I can see here is that all of these are player names. There's no other data getting in there. So that's great. So now we know that if we find a white space, we're going to be on the line with the player name. Now, the player name is basically the second item in our data. We have this number before it. So what we know is that we're always going to have a number, and then a new line, and then a player name as the beginning of our record. So what we can do is actually take our data and put it in a format where we can use that. So what we want to say is search for a number followed by a new line, followed by some text that has a white space in it. And for that, we're going to use a regular expression. These powerful text editors allow you to do searches with regular expressions. So if I bring up my search window again, it's this box that says grep. That's what allows us to use a regular expression for the search term. So for example, let's just start with something simple. I want to search for a digit. So I'm going to do \d. Hopefully you have looked at that regular expression handout I gave you. You know the \d represents a digit. And so now I'm going to say find the next one. You can see it's highlighting it in the screen back here. It finds the 2, and then a 0, and then a 1, a 7. It skips the dash and now goes on to the 1 and the 8. It skips these 2 lines because there's no digits there, and it's on to the 8. So that D is helping us find a digit. So we want a digit followed by a name. But we don't necessarily want just one digit, because if we were to scroll down, say, to the bottom of this file, we can see we've got 50 players here. We have a name, and right before that is the number 50. So we're going to have some number of digits. And remember that if you want some number of digits, you're going to do a plus. That means 1 or more. Okay, so we're going to look for 1 or more digits. So that'll give us a single digit. It'll give us 2 digits. It'll give us 1,000 digits if they're there, but there can't be anything else in between them, just numbers. And then we know we have those digits followed by a new line followed by the player name. So a new line we represent with a \n. And if we look for that, we can see that it's giving us all of our numbers with a new line afterwards. You can see here it only gets what's after the dot because the dot is not a number. Okay, so this is sort of working. Now what we have to do is put in the player name. Okay, so how do we find the player name? We need to come up with a pattern that's going to represent that. So we know that there's a white space, and there may be multiple white spaces. Some people might have a middle name. They might have a two-part last name like St. John. And so we know that the names are going to be letters, definitely spaces, and there may be a hyphen or a period. And that probably will cover all the names that we'll run into. So we're going to take our regular expression, and then after the new line, we're going to give the pattern for the name. So that name will be some set of characters that are letters, spaces, dots, and dashes. To have a group of characters like that, remember that we can put them inside square brackets. And so we're going to have letters, so we can say A to Z, or dots or dashes. And that square bracket says one of those, and we're going to have multiple. We also want to put a white space in there. And so this is going to say find one or more digits followed by a new line, followed by one or more characters that are letters, dots, dashes, or spaces. Okay, so we're matching a few different things now. If we start at the top, we do find our one line here, but then it's also matching 18, new line, EDM, because we have some digits followed by a new line, followed by some characters that are text, that are letters, spaces, dots, or dashes. So we need to refine our regular expression a bit. We know that names have a white space in them, and they all have white spaces in them. So what I'm going to do is copy this and then put a space and put that again. So what this allows for is basically some word, letters, dots, dashes, could be a space. We could have a two-part first name, but there has to be a space that comes in the middle somewhere, and then another set of text, which could be the last name, but we allow there to be a space in it in case the last name has a space. It's a two-word last name. Okay, so now we're going to search for that again. And if we go through our file, it looks like that's working correctly. We're getting every player and their number in the list. Okay, so now we have a regular expression that looks like it's going to find all of our players. Now what we want to do is turn that into some recognizable thing that's going to be the start of our line. Okay, so let's start by just putting that all on one line as it is. So we've got our digit and then our player name. We're going to put the digit or the number in parentheses. So it could be one digit, it could be multiple digits. We're not going to need that new line. We want to put these all on one line. And then I'm going to put the whole name in parentheses. What that allows us to do, which you should have seen if you read the notes, is refer back to those things in parentheses. So \1 is how you do this in most text editors. That refers to the first group of parentheses. So basically those numbers, we're going to replace this with those numbers and then a tab and then the name, which is contained in our second set of parentheses. So we find this whole thing and then we replace that with the first part and a tab and the second part. If we do that in the whole file, you can see the one player we were looking at here is showing up now on one line as our first player. Now what we have to do is get all the other stuff onto a line with it. So basically move all of this back up here. Okay, so that's a little bit trickier because we need to basically be able to not move this line of text up onto the previous line. We can't just get rid of all the new lines. So that might suggest we want to approach this problem in a slightly different way than we did. So we know that we have this digit followed by a name. Let's undo that replace that we just did. So we're putting everything back like we started. Now, no matter what we do, we're always going to have that digit followed by the name. The pattern that we were using to find that was digit, new line, name. But what if we get rid of all the new lines? So what I'm going to do is just replace all the new lines. They're represented by an R in this file, and I'm going to replace them with tabs. Now that gives me one big line that has all the text on it. And if I scroll sideways, you can see that there's multiple players. Here's another player, 4, his name, and then all of his stats. Here's another player, number 6, his name, all of his stats. Now, let's use that same regular expression where we said, well, we know we have a digit followed by a name, and we can easily find the name because it is the only thing that has a white space. And we're going to put a new line in the front of that. So if I put our regular expression back in there, we said look for a digit or a set of digits followed by a new line followed by the name. Now, we don't have the new line anymore. We have a tab, but this should still work for us because this white space here is always going to find us the name. So if I start looking for this, what we can see is that we're getting each individual player. And so now what we can replace that with is a new line followed by the first thing, the digits, followed by a tab, followed by the second thing, which is a name. And if we do replace all, what we have now is a nicely formatted document. This is tab separated. A really nice thing about tab separated files is you can literally copy and paste the text into Microsoft Excel. So I just copied that, pasted in here, and now we have this nice table of data. This is a good step to do because it allows us to go through and check for any errors. So we can make sure that all of our columns line up. Everything looks really good here. And so now we've taken that file that was just a string of numbers and put it into this really nice structured format. Just so you can take a look, we got that by copying and pasting the data off of this page, this NHL statistics page. You're actually going to do a lab on web scraping, which you can do in a much more sophisticated way than what I just did. But it's a similar idea in that you want to look for patterns in the text and use regular expressions to find things that you know are indicators of being in the right place, and then expand out around that in order to get things into the right format. Regular expressions are a little bit tricky. You really just have to practice with them. I gave you a couple pages of notes, which is basically everything you need to know, but just like with any programming, you don't get the handle of it just by having read text about what it is. You need to actually get in there and do it. So you're going to try some exercises with this, and the more you use your regular expressions, the better you're going to get at that. Regular expressions are a really critical tool for data science because so much of your time is spent wrangling data, taking stuff that's in one format and trying to get it into another one. And oftentimes, if you have specialized formats, there's not going to be any clear way for you to use an existing tool to change the format. You're going to have to write a tool yourself. Regular expressions are typically the way that that's done. So you want to practice with those a lot. Whatever programming language you like to use will support them. I tend to write a lot of my code in Perl, which is like not the most useful tool if you want to get a job. Most people aren't looking for Perl skills, but it's super useful for processing web data. But Python absolutely can do regular expressions. If you're a Java or a JavaScript person, you can even do regular expressions in there, though they're a little bit clunkier. Any language you want to use can handle regular expressions. So it is absolutely worth your time to really play around with those. There's tons of exercises online besides the ones that I'm going to give you to start getting practice with extracting data from unstructured text by using regular expressions. So that's it for data wrangling. That gives you a little bit of a taste of how we might do that. I'm going to give you a couple simpler examples than what I just gave you that I want you to actually try in your text editor because that's a nice, easy way to get a handle on regular expressions that very easily translates over into doing it in a programming language. So that's not anything you have to turn in other than posting on the discussion board. I just want to see you all practicing with it a little bit, and then you'll get another handle on this when you look at web scraping in the lab.